Good afternoon. I'm Claudia Gutierrez. I'm postdoc at Pinca postdoc at the University of Turku, and today I will talk about a peculiar supernovae node. Okay, so my main research focus is in core-collapse supernovae, and just a brief introduction. Core-collapse supernovae are produced by the explosion of massive stars. So we classify them based on the lines that we see in the optical spectra, and the main classification is between type 1 and type 2. In type 2, we see the hydrogen lines, as we can see this part here. This is a type 2. And in type 1, we don't see hydrogen lines, but we can see another different lines, and then we have some subclassifications as type 1b, that we see helium lines, and type 1c, that we see a weak silicon line. We also have a transitional object, type 2b's, that at the beginning we see the hydrogen lines, but after some days the hydrogen lines disappear, and we see a helium dominates the spectrum. So these lines can tell us about the mass loss that the star experienced before the explosion. And in the middle panel, we see that in the case of type 2 supernovae, these stars retain a significant amount of hydrogen at the moment of the explosion, and that's why we see the hydrogen in the spectra. While if you go down, the mass loss increases. And in the case of type 1c, these are very stripped stars, where the hydrogen and the helium envelope were removed. So if we go to the spectra, there is a large diversity. In type 2, we have objects with a plateau, so quasi-constant luminosity for a few months. We also have some objects like 87A that just go down, up. The rise is very long, around 90 days. And in the case of a stripped envelope supernovae, type 1bc, we have a bell-shaped light curve. So this is the standard classification, but then as we have more objects, more telescopes, this diversity increases, and we have now some objects that show these narrow absorption lines here, and they are called type 2N, then is for narrow. We have also these 1BN, narrow helium lines, and 1CBL, the lines. So the spectra is similar to the 1C with the silicon, but the lines are very broad. But if we go to the spectra, so we also have some peculiarities. So on the bottom, the background, you see the normal or the usual light curves of these type 2s, 87A here, and then extreme objects like these two. In blue is the IPTF 14HNLS that has multiple peaks, and in orange is OGOL 14 supernova 73 that is very luminous, and the rise to the peak takes a lot of time. On the other hand, in the stripped envelope, we also have a large diversity in luminosities, in the rise time. Also, we have double peak light curves like this one, 93J. So we want to understand what is happening. As a part of the IPESTO collaboration, that is a collaboration in Europe and using the facilities in Chile, I started the follow-up of hydrogen-rich supernovae in low-luminosity hosts. Why? Because I realized that in these environments are these kind of extreme and peculiar objects. So here you can see some of the galaxies that we have for these objects. And all these observations started in the south. But in the north, we didn't have like a collaboration to follow the objects, and that's where nuts appear. So Max did an introduction, and since 2018, we have these 8 objects. On the top, you can see the type 2 supernovae, or the hydrogen-rich. We have fast declining, long life, with interaction, 87A-like. We also have type 2b, double peak 1c, superluminous supernovae. So in this case, the spectrum is similar to 1C, but they are very bright. And we have like a bonus that is a fast blue transient. So I will go just very quickly to some of them, explaining what they are so cool. So this is a type 2 supernovae. And as you can see, the light curve is not similar. It's quite different to all objects that I showed before. So has a decline, then goes up, has some bumps. The important part here is that we have the spectra, and that was after 174 days. And the first spectrum looks like a type 2 supernovae a couple of weeks after peak. So something weird is happening in this object that has a very slow evolution. And for that we have, well, the light curve with knots. This is just with the atlas. And we have also the image of the host galaxy and the spectra. There is this another type 2, 18H8Y. In this case, we have like a bit of problem because we have the object when it's already declining, but we don't know if the explosion was just a few days before or months, and that is because the supernova was behind the sun. So we just observed or detected in that moment, but if we see the spectra, it's also consistent with a very young supernova. So we need to see if it's similar to the previous one that has a slow evolution, or if it's really the explosion happened just a few days before. This is a 18HF MET. This one has an interaction, as you can see in the spectra. The P Cygni profile of H alpha is quite normal up to 40 days, but after that is dominated by a broad emission and then a very peculiar profile. The light curve is going very fast, decline very fast, but after 60 days is flat, and in some bands is going up, that could indicate some kind of interaction. This is a 1C with that double peak light curve. It's quite good because before this one were only two objects with similar light curve morphology. So basically it has a first peak that lasts about 25 days, and then the supernova goes to the main peak around 50 days. The spectra are with different colors, and this is because we are pointing the phases. So first peak is blue, main peak is orange, and the tail is green. So we can see that the first spectrum is consistent with a 1C. We see the silicon line evolves, the silicon line disappears, but then when the supernova is again in the peak, in the main peak, the spectrum is similar to the first one. So something is happening in this object that produces or gives this extra power. So with all these observations were with knots, but the good thing is that we have a very nice coverage, and we also work with people working in modeling. So for this object, we work with two different possibilities. One is a double nickel distribution. So basically you have the nickel in the center that powers the main peak, and some shell or nickel in the surface that basically power the first peak. On the other hand, we can have a configuration that could be nickel plus magnetar. So the nickel powers the first bump or peak, and then the magnetar is responsible for the second peak. In this case, it was very difficult to know which one is the best one. However, the reddening was a bit confusing for this object, and we believe is much brighter. If that is the case, we favor the nickel and magnetar model. So Max was talking about this object. It's a superluminous supernova, 20 WNT. As you can see, we have a lot of data with not both in the spectra and the photometry. So the object was very peculiar, has a very slow rise to the peak, but has a bump at the beginning, as you can see in the small square there. So goes to the peak in around 80 days, then decays, following the cobalt decay, and then has a bumpy light curve. In the spectra, the evolution is very slow. It's consistent like with a 1C, and it's not changing for months. For this one, we also use modeling, and we compare again magnetar, radioactivity, and we also propose a CSNF scenario, but for this one, we don't have a model. So in this case, we have in the left the powering by nickel we have two different configurations of star, but at the end we prepare the very massive star that produce around 4 masses of nickel, because when we tried the magnetar, it didn't work. So for this object, we favor the radioactivity powering. However, we said that CSM is also a possibility, but we don't have the models for that because the object is very extreme. And finally, as I say, the bonus, we have this blue transient, CSS 161010. The object, well, was followed in 2016 by NATS mainly. The object goes to the peak in less than 4 days, and after the peak declines very fast. 75 days is already gone, and it's quite luminous. So when we compare with similar objects, that they are very few because they are very fast, so it's difficult to identify them, we see that the light curves are very consistent with the most popular object, that is 18 Cow, that is there in purple. So it's consistent in the different bands, and the colors are also quite similar. The good thing of this object is that we have a spectral sequence, thanks to NAT and other sources. So, and in this case, we see that we can identify, in principle, the hydrogen lines. But there is a problem, and is that the hydrogen lines are blue shifted by a lot. So now we are working in the modeling, trying to identify what kind of object can produce this, because it's very complicated to have this kind of broad profile and always blue shifted. But was a paper published on the same object in 2019 with the X-ray and radio data, and they have some scenarios that is a TDE with an intermediate mass black hole, but they don't reject the idea of an stellar explosion. So these are the objects that we are following. And just to summarize, I want to say that thanks to the NATS, we can follow these peculiar objects. The quality of the data is very nice. We have an excellent coverage, so we can characterize these objects in a good way. We also have polarimetry. So in our group in Turku is Dr. Takashi Nagao that leads this part. So for these objects, some of them, we have polarimetry. And as I say, we work with people that makes models. So the collaboration with that is very good. And thank you very much.